All right. So now, given that we think that charge conservation is um, is has like deeper roots than Ampere's law, we're going to start with it to try to figure out how to adjust Ampere's law. So let's grab the charge conservation equation. Okay, so still we start with that. And so furthermore, we have Gauss's law. So let's grab that as well. So what we can do is basically plug Gauss's law. So this charge density into this. So this is the charge density. So this is equal to minus the derivative with respect to time of the divergence of d minus that. Okay. So and then we can change the order of the action here. So we're gonna make it the minus the divergence of rate of change dt of d. And then we're gonna bring this over to the other side. So divergence of this combination d hat is equal to 0. And this is something referred to as current continuity equation. It's equal to 0. So that this divergence definition, this definition of divergence, is this surface integral. So we're going to do that, j dot d dt ds is all sort of definition of divergence over the volume in the limit as the volume shrinks close to 0. So we're going to change basically this equation to the definition of divergence, where S is a closed surface. And then we're going to, we can just separate them out again. So limit delta V goes to 0. Integral of j dot ds hat over delta V is minus limit of delta V going to 0. Surface integral of derivative of d with respect to time over the surface over the volume. So this, we can bring the derivative with respect to time outside. By ds over delta V. And then people defined this thing as a parameter. This is, I believe it's pronounced something like psi or psi. It's another Greek letter, and it's defined as the electric flux density. So you end up with del dot j hat is minus the rate of change of this psi of E equal to that. So let's see. Yep. Okay. So basically that's the modification that now we can sort of plug this in to those equations and end up with this. This is what Maxwell came up with. And the good thing about this, basically, it's relating two things together, or it's saying that we have two aspects of electric, or two types of electric current. So one is here. This is current current density. So again, J is defined as I over A. But A is the area of whatever the current's going through. So this is, you only get current in conductors. So current only in conductors. So it depends on the conductivity of the volume and so on. This, on the other hand, is also, a current, but it's completely independent of conductivity. So you can have this, it can exist in a vacuum, can exist in a dielectric, etc., and it's also called the displacement current. Okay, and this was the sort of continues to be sort of the Maxwell's contribution to these. Okay, so let's continue to look at how this is useful. So like now we have to kind of imagine another experiment where we have a loop, like let's say a wire. So this is a conductive loop. And there's a current source in this loop. So the current source is forcing a current I0 through this. And let's say we define a loop around this, sort of a lasso, to basically to try to figure out our magnetic aspects of what this current's doing. And um, let's say we look at so this is the loop, and let's say we just look at this surface enclosed by the loop. So let's call that the S1 surface. So if we and let's take the direction of this line. Let me draw a bigger line so it's a little bit more obvious what I'm doing here. Let's go to that. So we're taking a loop, and that loop has a certain direction. So say we use our right hand rule to take in that direction, and then around the loop we start first looking at the surface S1. That's related to that loop. So if we take the line integral of the magnetic field around this loop, we'll come up with what is the magnetomotive force. So if we take the integral, so integral of magnetic field around this counter. This gives us the MMF, which is the magnetomotive force. And that's equal to the current enclosed inside the path. In this case, that would be I0. So the current in the surface S1 is I0, and there's a symbol for the magnetomotive force. Looks like a wide U around this contour C. So C is the loop around which we're going. So this current is equal to the integral of the current density times d sub s1. That's equal to this MMF, which is taking the integral along this contour of h dot dl. Okay, so that's all stuff we've looked at in terms of Ampere's law. Now, let's say nothing prevents us from taking another surface. So the surface S1 is a surface that is defined. The opening of S1 is, or the edge around S1 is defined by this contour. But we could just as easily take another S1, or another surface, call that S2, that looks very different, but is still, the opening of it is still defined by this contour. But let's say we take this part of S2, call that S2, sorry. So let me put that in a different color. So let's say we pick this outside area and call that S2. And so the current enclosed by that should be fine. So because, so let me just redraw. This is, if I flip it around, this is the contour. This inner surface is S1. This outer surface is S2. Now, since the MMF, this U parameter, U of C, or Ampere's law, is only dependent on the contour C. It doesn't matter if, so we can either use picking S1 or S2 as the surfaces should give us the same result. Because the only thing that matters is the line. Now, whether that line, the surface we pick for that line is that enclosed line is this inside surface or this outside surface, either one should give you the same result. So in this case, MMF is equal to I0. Okay, so that's fine. Now let's say we change this experiment. So far everything's good. Let's say we change this experiment a little bit and stick a capacitor in series with this line. So let's say, so change experiment. So we still have the loop with I0. Now I'm going to put a capacitor here. And I'm still going to have this I0 for a while. And let's say this capacitor has no leakage, current leakage. And let's say I define my contour here, my contour C. And again, S1 is just inside that contour, and S2 is still this bigger loop around. But now let's say this S2 encloses just the top half of this capacitor. So this sort of shows us the problem with Ampere's law, because again, S1 and S2 should both give us the same value, but so S1 still the electromotive force around S1. C around S1 still gives us I0, because that is, still enclosing I0. But the problem is now, if we, with this new setup, if we look at the surface S2, the electromotive force around S2 ends up being 0. So these obviously are not the same. So which it causes a problem, because um, just by picking it, in this situation, just by picking a different surface, we've got to a different result, which this tells us there's like something missing in Ampere's law, because this is Ampere's law, and just depending on the surface I pick around the circuit, I seem to be not getting to the same answer. So again, so all this stuff's pointing to the fact that there's something missing in Ampere's law as it was before Maxwell. So one thing that can help us get to an answer is if we look at just the top of this plate. So if I redraw this capacitive plate, if I redraw it, expand it out, so that's what the capacitor looks like. Zoomed in. Current I0 is coming in and dumping charges on the top plate, meaning that our charges going to be accumulated in the bottom plate. So, and if we have charges accumulated, we know we'll get an electric field. Or let's just say we get a D field, so we get a change in the charge density, which now we get a change in the D field, which gives us a change in the electric field from the top to the bottom. So this is the electric field from the top to the bottom of this capacitor. So basically, we have this change in E field. We have a changing E field in the capacitor. I guess you can think of it as like going in different directions back and forth is equal to minus I of S. Okay, and this is the current continuity equation, which we looked at over here. So again, we have this is what is referred to as the displacement current. So this thing is, again, the displacement current. And the reason this is important is it allows us to have, that allows to relate, so it relates a changing E field and B field even when there are no conductors. For example, in free space, or like example, free space. So if we add this to our final form of the Maxwell's equation, we end up with the following. So we still have Faraday's law didn't change. So that's del cross E. The curl of E is change in the magnetic field with respect to time. Gauss's law didn't change. So that's del dot B is equal to 0. Del dot D is the current density, and B is mu naught mu R H, and D is epsilon naught E. And then we have the charge conservation equation, which also did not change. What did change is Ampere's law, which is that the curl of H is equal to current density plus this displacement current. this is the full form of Maxwell's equations. And this was really a critical thing, again, because um, imagine if you didn't have this, right? You still, the previous equations still related the electric field to the magnetic field. So it changing the state of the equations as they were before Maxwell still related a changing electric field to a changing magnetic field and vice versa. But they always, because it was only this current that was showing a changing charge or electric field, the actual current in a conductor, these would only be valid inside or in relation to a conductive wire. So as long as you have a conductive wire, and that's where your current would be flowing, you would have this relationship with electric field and magnetic field. What Maxwell did with this definition of this displacement current is now you can have a relationship between a changing magnetic field with a changing electric field even outside a conductor. So that, for example, when you are transmitting a radio signal, so those are electromagnetic fields traveling through space, and the changing electric field is causing a changing magnetic field and vice versa. So you have this wave that's created that propels itself, or when you're thinking about a um, light traveling, again, it's traveling through space. It doesn't need a wire to travel through. So this is why this was very like a very critical addition. And basically this allowed the modeling of and sort of the idea of that there could be such a thing as an electromagnetic wave. So a very, very critical result by Maxwell. And then that basically made this final form of these equations, really these sort of four equations. These guys are more like definitions. It's really these four equations that are called Maxwell's equations and these allow the concept of a traveling electromagnetic wave.